Hey everyone, it's Ross. I'd like to go over a mini lecture for Lab 10. So last week we talked about standing waves on strings, and a lot of the same properties will come back this week because we're talking about sound wave interference when you have two speakers facing each other. And so in a lot of ways, you can say it's really close. It's a pretty good analog for having, that reflection on the hard fixed surface. So here, what you want to think about is there's two speakers. You space them out appropriately, and you do need them to be, far enough away that you'll be able to get some good data. Not too close, not too far. So we still need to be thinking about frequency, wavelength, and wave speed. And so I've sort of drawn here, as you can see, sort of the way we visualize the waves. They sort of start close and then they get farther and spread out to indicate that they're decreasing in intensity. But here, they're going to overlap, right? They're going to interfere because of the way they combine. So let's think about, what if they were playing a pure tone? So I'm going to play a pure tone for a few seconds. It's going to be a G4. So it's roughly that 392 hertz. And they're in phase, so there's no offsets besides how they're spaced. That's important because you do have to keep track of all these things. So let's just give it a listen real fast. And that's my daughter, if you hear in the background. Okay, so hopefully we all have an idea of a pure tone. Sort of just a nice note, or maybe a not so nice note, depending on how high or low the frequency is. And so let's keep that picture in mind, right? So if you haven't seen already, please check out the lab setup or the sound interference setup number 1 video that I post on YouTube as well. And let's keep going. So let's once again think about how many wavelengths fit in between them. So with the string, it was more about how many could fit in between where it was fixed. Here now it's where the speakers are sitting, right? Because they're fixed. And so you can see sort of here, just think of that as the face of the speakers that are producing the sound. And you can see that here I've drawn in gray the waveform for the sound produced by the right speaker, and in black I've drawn the waveform for the wave produced by the left speaker. And you can see here, because of the way they're spaced, they're going to equally align up to cancel out into a pure destructive state, or a flat line in the waveform. This means you would get something that's either inaudible, completely quiet, or really, really, really quiet. It just sort of depends on how off anything is here. If the ground's just like a little uneven or anything. So what you want to keep in mind here is I have them spaced out exactly a whole number of wavelengths. In this case, the wavelength takes up 8 grid squares, and so it's 24 grid boxes, or 3 wavelengths. That's important if they're in phase. So anything I say is going to be for the signals themselves being in phase, no additional offsets, and or at least the way they're played. And as you can see here, this looks out of phase because they're facing each other, right? They're pushing waves towards each other. And so their setup is what causes them to be out of phase, not anything else. So once again, that's really important to make sure we don't have to think through anything, crazy complicated. Okay, so if you look at these waves, you can see like, oh, what if we just shift one over? Or both a little bit over. It's easier if you fix one and you shift the other. So if you shifted, let's say the right speaker here, over a quarter of a wavelength, that's a half a wavelength, you would get pure constructive interference. If you did a quarter, if you did anything other than a half, or so many halves, you would get some sort of weird in between, right? So if you go exactly 1/2 either direction, you'll get a pure constructive interference pattern. And the thing to note then, right, is that you see this sort of doubling effect. You see some loud and some quiet zones. But the other thing to think now is now they're not, so 6/2 is 3 wavelengths. Now if you put an extra half a wavelength away from each other, you get this pure constructive set. So this is something that, this is what makes it mathematical, this is what makes music mathematical, is that you can sort of play with the numbers to build stuff or get some sort of interesting effect. So for this lab, for setup number 1, right, you're trying to find, you're taking your microphone, your sensor, and you're moving it around, and you're trying to find for the tone you spit out, you set, they spit out, or the wavelength, because they go together, and for the wave speed, so because it's sound that's pretty well established, you can determine based on your measurements between loud zones or quiet zones, or loud and quiet zones, what that wavelength is, and you can say, how does that match compared to what it should be, because I'm producing sound at a certain frequency. And this is all, the speed of sound is variable if it's humid or warmer, but we're just sort of going with the average number, and that's about 343 meters per second. So that's something to think about, like whenever you're spacing speakers, if they're going to point towards each other, you can sort of position things where you want it to be loud or quiet. This is the basics behind sound engineering a room, or a concert hall, recording studio. If you want to sort of have like a a club or sort of a restaurant that has like a dance area, and then the restaurant seating, you want the music quiet but probably still audible. But when you're on the dance floor, right, you want it to be kind of as loud as it's going to be. You don't want it to be super quiet on the dance floor. No one's going to want to dance. Okay, so hopefully everyone's got a pretty good idea of the way the waves are interfering, how it's similar to what we talked about last week, but different at the same time, and what sort of measurements you would take, and what sort of tone you would be listening for a high, and so just to go back through again, we're still talking about waves interfering. You have to choose a frequency to play, and if you know the wave speed, you can predict which wavelengths it has, and if you do or you don't, you can say, okay, let me measure based on the setup where the highs and lows are, and I can do that to get how much a wavelength is, and then compare it. So feel free to ask any questions, send me an email, join the Zoom link. All right, thanks everyone, bye.